Okay, so how do you save 200 megabytes of memory using literally one single line of code? I know, it sounds a bit like clickbait, right? But if you're out there building data-heavy applications with millions of objects, knowing the answer to this exact question could genuinely be the difference between a production system that scales elegantly and one that just crashes and burns from memory exhaustion. Welcome to this explainer on Python's advanced internals. Today, we're doing some senior level deep dives. Our goal is to completely demystify those intimidating under the hood concepts that often act as gatekeepers in high level engineering roles. We're taking the magic out of Python, popping open the hood and looking right at the engine itself. Consider today's agenda your ultimate survival checklist for a senior level FANG interview. We'll be hitting memory and garbage collection, optimizing with Python slots, mastering Python metaclasses, the descriptor protocol, and finally, asyncio event loop internals. Let's just jump right in. Starting off with Section 1, Memory and Garbage Collection, which is really the absolute foundation of resource management. Because before you can truly optimize or profile any application for production, you have to understand exactly how Python decides to keep your data alive, or, when it decides to destroy it. So Python uses automatic memory management. You can think of it like a highly efficient self-cleaning system. Step 1, every single object inherently tracks how many references are pointing to it. When that reference count hits 0 in step 2, the memory is freed automatically in step 3. Simple enough, right? But what if two objects point to each other, creating this infinite loop where neither count ever reaches 0? Well, that's where step 4 kicks in. Python's built-in GC, or garbage collection module, actively steps in to clean up those stubborn circular references. Let's actually look at the standard sys module in action here. We create a simple list A and point a second variable B to it, so the reference count is now 2. But interestingly, when we run sys.getRefCount, it actually returns 3. Why? Because passing the variable into the function itself briefly creates another reference in memory. It's a fun little quirk. As we use the del command to drop these variables, the count naturally drops, and ultimately the object is freed. And if you ever need to manually force the cleanup of those cyclic loops, you just call gc.collect explicitly. All right, moving to Section 2, Optimizing with Python slots. Now that we've got memory clearing down, let's talk about actively defeating memory bloat. This is where we answer that high-stakes question from the very beginning of the explainer. By default, Python objects are incredibly flexible, right? They store their attributes in a standard dunder dict, a dynamic per-instance dictionary. That flexibility is awesome during development, but dictionaries are notoriously memory-heavy because of all the underlying hash table mechanics. The alternative? Python's dunder slots. By defining slots in your class, you completely replace that heavy dictionary with a fixed array of pointers. Yes, it's more rigid, but it is incredibly lightweight and gives you much faster attribute access. Making this one single shift in your data model can reduce your memory footprint by an absolutely staggering 40 to 60%. If you're running a massive application like high-frequency trading or a web scraper with millions of active instances, this is a literal game changer for your infrastructure overhead. And the math here is undeniable. When we use sys.getSizeOf on a standard dictionary instance, it takes 48 bytes for the object itself, plus a massive 232 bytes of overhead just to maintain that dynamic dictionary structure. But look at the slots instance, just 56 bytes total. Scale that up, and using slots saves approximately 200 megabytes per 1 million objects, literally all from adding that one single line of code at the top of your class definition. Okay, let's raise the stakes a bit for Section 3, Mastering Python Metaclasses, or as I like to call it, Building the Factories. We are moving into the real object-oriented internals now. I know metaclasses have this reputation for being super intimidating, but let's strip all that away. A metaclass is simply the class of a class. That's it. Just as a normal class acts as a factory to create individual instances, a metaclass is a factory that creates classes themselves. In Python, type is the default metaclass. By writing a custom one, you can actually intercept a class right exactly as it's being dynamically created in memory. Check this out. If we want to enforce a strict singleton pattern, we can create a singleton metaclass that inherits from type. The real magic happens when we intercept the class creation process inside the dunder call method. Every time the class is called, we check an internal dictionary. If an instance already exists, we just return it. If not, we generate it. Why does this matter? Well, by setting a database class metaclass to singleton meta, we guarantee that no matter how many times we try to instantiate that database, it will always be the exact same instance. This is exactly how you manage crucial resources, like database connection pools, without leaking memory. Section 4. The Descriptor Protocol. We've looked at how classes are built from scratch, so let's shift focus to how their individual attributes are strictly controlled. Descriptors are basically the secret engines running the decorators we use every single day. If an object implements dunderget, dunderset, or dunderdelete, boom, it's a descriptor. This is the exact hidden mechanism powering built-in tools like @property, @classMethod, and even when you write your own complex custom decorators with arguments. It's also the magic driving object relational mapping fields in heavy enterprise frameworks like Django or SQL Alchemy. Now, the absolutely crucial rule of hierarchy you need to remember here is this. Data descriptors, meaning descriptors that implement the dunderset method, always take priority over the instance's own dictionary. This rule is paramount. It ensures that when you write strict data validation for an attribute, no other developer on your team can accidentally bypass your validation by just injecting a value directly into the dictionary. It acts as an unbreakable guardrail for your data integrity. All right, for our final deep dive, Section 5, Asynchrono Event Loop Internals. Let's bring the cognitive load back down to practical concurrency. We're transitioning from managing memory and objects to optimizing time itself. The asynchronous event loop is basically a highly tuned, single-threaded scheduler. It manages your coroutines, handles I/O polling via system selectors, and keeps track of timers. Think of it like a really efficient restaurant kitchen manager. They are just one person, single-threaded, but they perfectly coordinate all these overlapping tasks, checking the oven, queuing up orders, telling the chefs when to start, all without ever just standing around, waiting and doing nothing. The event loop operates in this continuous, incredibly fast cycle. First, it queues up any ready callbacks. Second, it pulls for I/O completion, checking if network requests or file reads are done. Third, it schedules waiting coroutines to run as soon as their I/O is ready. The absolute MVP here is the await keyword. It suspends a single task and immediately hands control back to the loop, keeping the whole system moving forward without ever blocking the main thread. Because if that main thread blocks, your entire application freezes. So, we've unmasked the secrets of garbage collection. We supercharged memory scaling with slots, built untouchable class factories with metaclasses, locked down attributes with the descriptor protocol, and orchestrated time perfectly with the asynchronous event loop. So, which of these powerful internal mechanisms will you leverage to optimize and scale your next Python production app? Whether you're profiling and optimizing code for production, implementing custom context managers, or reworking your data models, the knowledge to build highly scalable, senior-level architecture is now yours. Thank you so much for joining me on this explainer. Now